Welcome back, everybody. It is Tuesday night, and that means another episode of Theater and Tech Trends. And the focus is on the theater this night because I have a good friend. At least I think he's a good friend. Hopefully he thinks the same of me. But an awesome guy, Anthony Grimani, and he is going to tell us everything we ever wanted to know about acoustics, but we're afraid to ask. And for those that get the reference, good on you. Also making his first appearance in 2 or 3 weeks or something. I don't know. We have my illustrious co-host, Digital Don AV, wearing his accoutrements of glory.
I couldn't miss. Yeah, I'm sorry. I don't like to be seen in it, but
I've got you look amazing.
I've got elastic pants because I can't buckle or button my pants. I've got a fanny pack to carry my stuff. And I wear flip-flops. I'm like an old man in a neck brace. I am. I need a walker.
Well, we are just happy that you can neck brace it up with us here tonight. So, Don, welcome back to your co-hosting duties. All right. Now, before we dive in, and Anthony he's ripping and rearing. I mean, I'm excited for this because we are going to be learning. We can sit at the feet of the master, right, and learn, because this man has done it all and he knows what's going on. But first, everybody out there, if you have questions, please throw them up. I'll get them up as we go along. And don't be shy. We got HiFi Haven out there. Van Gool has joined. Mr. Piranha is with us. The Haven, of course. So good to see Don. Don, you're getting your love. But with that, everybody out there, thank you for joining. And Anthony, tell us a little bit. Well, level set. Let me take a step back. Let everybody know who you are, what you do, and why they should care.
Who am I? Boy, there's a bunch of different ways to put that. I'm a buddy of Jiles McCoy and Digital Don.
You said it.
That says it all, right?
I think I really pushed the levels of the microphone just then.
Actually, we just before we got on the show, we were talking about levels. Do we all sound the same? So if you guys listening out there go, whoa, Anthony's like really loud, I usually am, or whatever, just let us know. Hey guys, great to see you, Don. Yeah. Anyway, let us know if our levels are good because I care about that stuff. So who am I? I'm just a guy that's been loving sound and music and film for years. I was born into a family where that's what was done. My dad was an engineer. My mom was an opera singer. So I've just been doing this a long time. I did study formally electrical engineering with a focus on audio and communications. I was lucky enough right out of college to go get a job at Dolby Labs, working originally on noise reduction chips for cassette deck. Remember those things? And then got very, very early involved in the surround sound technology that eventually led to ProLogic and then Dolby Digital. And after a while of doing that, I was recruited over at Lucasfilm to start the Home THX program. Did that for about 10 years. So all these products you saw out there that had a THX logo was something that I probably worked on with the licensee, with the designers, with the engineers. And then 25 years ago this year, I left that cush job in the corporate world to start my own company. And that company does design and engineering services for high-end home cinemas. I call them home cinemas or screening rooms rather than home theaters. Call them whatever you want. A place where you sit down and you watch an amazing movie, listen to amazing sound, and get completely transformed and transported in there. And some studios and some post-production facilities and some performance halls, a bunch of different things. But the main core of it is designing really cool home cinemas around the world. So along the way of designing those, there's two spinoffs. There's one company that has decided to make its own loudspeakers. It's called Grimani Systems. Down there, it says that name, which is kind of a new approach, kind of a new generation of loudspeakers for the 21st century, is the thing we like to say.
Don't get a big head now.
Yeah, really. Thank you. In Okinawa.
We got that smile out of him. I love it.
Genki desu ka? And then another spinoff, which is, well, the world needs a nicer, better organized solution for acoustical treatments, which is what we're going to talk about today. Acoustics is complicated, and learning it all is like just trying to figure out how to juggle with 6 balls and a chainsaw that's running, and then a flaming torch all at the same time to keep track of it all. And we kind of thought, we being, partners, and I decided, there's a way to packetize this to where the recipe can be presented to people. We'll talk about that. And then you can just go get these components, put them up per the instructions, and end up solving your acoustical issues. So I always like to start these things with, hey, you guys out there, what are your pain points around acoustics? Those of you who have bought really nice speakers, really nice amps, all nice cables, nice surround decoders, all the stuff, you put it all together and you're like, it doesn't sound as good as I want it to. I'm hearing this in the room or whatever. So maybe I'll take one person going, this isn't working. Dialogue's not clear, or I can't hear the surrounds or whatever. I always like to start with that.
Right on. And while hopefully if all these people out there, somebody throws up a question, I have one if they don't. But I did want to comment that, you said you could call the room whatever you want to. Well, I once referred to my room as my pleasure room, and it did not get the response that I was anticipating. So
yes, everybody's minds are twisted into the wrong thing.
Absolutely.
Pleasure should just be audio video.
Your victims didn't like it.
So here's a challenge. So this is not the question you were looking for. Double A is like the Knicks and Pistons game. So square. My room is square. And it seems like the biggest nulls are always right in the middle for bass, right where I want to sit at every time. So that's my challenge. And, everybody else out there, please type in your challenges. But what can you do about square rooms? Is there anything to be done other than knock down walls?
Just move. No, actually. So that topic alone, I could talk for the next 3 hours. Warning. I'll bring it really short. If the room is really square in that the acoustical impedance, what the sound waves find from the left wall, that's my left, I guess you're right, the right wall, the front wall and back wall are actually identical. So it's square. And the ceiling and floor are, is it a cube or is it actually square with a different height?
It is not a cube. It is about 14.5 by 14.5. And then about 7 feet tall. This is in the basement.
So a nice multiplier, right? And what is it made of? Is it concrete or is it American made, what's called gypsum board on studs?
It is some of the walls are concrete with studs, then drywall, and then there are some walls that are just drywall into another space on the other side.
So this is that place where I'm talking about spinning a lot of different sticks and juggling a lot of balls. So the junior acoustician would say, oh my God, you got a square room, it's going to be terrible. Well, in reality, the impedance, the actual character of what the sound waves hit on one wall is different than the other, because one's studs with concrete behind, the one is studs with air behind. So in fact, for visually, your room is square, but acoustically, it's not.
Right.
So what would happen is if it was square acoustically, which is, let's just pretend your room was all built of 12-inch concrete all the way around, and the lid and the floor are all solid to where the waves had nowhere to go, and that your main entrance door is this 300-pound slab of heavy steel to where it doesn't bow and buckle. You got a problem, because now the sound bouncing back and forth from left to right and front to back create what's called resonances, also known as room modes, which I don't like to use that word, but standing wave resonance, which means that the sound bounces back and forth and it causes this kind of thing going on. And in the middle of the room, there's a null.
Yep, because the troughs match up, right?
There's a trough that matches up. I have a different lecture where I actually show a really nice little animation of that. But there's a hole in the middle of the room at some sets of frequencies at the first harmonic, in which the wave is twice as long as the room. There's a trough. And then when the waves are 3 times or 1/3 of the size of the room, there's a trough at 1/2, but also a quarter. So there's more troughs. And then when the wave is the length of the room, there's a trough at 1/4, and 3/4 of the room. Actually, what I said earlier was wrong. So there'd be a trough at 1/2, and then that half is split in 2. And so it gets a little complicated in the number of peaks and dips. Main important troughs are like the first, second, and third harmonics of the initial resonance. That's if the room is all concrete. And what you're going to hear when you're in the middle of the room is a bunch of frequencies are missing. Does that mean you got to move? No. Because in a room like that, which is not what you have, but in a room like that, you actually know exactly where the resonance frequencies are. And they're very well disciplined. They're terrible, but they're all terrible the same way.
They work according to physics, right?
According to physics. So what you can do is you go, okay, I have a problem at 36 hertz, and I have a problem at 72 hertz, and you can actually build what's called bass traps, actually things that absorb bass at those frequencies and resolve your problems. Most rooms are not like that. Most rooms have standing waves that are like odd multiples because the wall's buckling this way over here and doing this over there. But if it was all concrete, all bets would not be lost. Instead, you actually have known errors that you can fix, number one. Number two, in a room like that, you can place 4 subwoofers into 4 corners and tune them with relative delays, changes of levels, and slight EQ changes to where the standing waves are sort of contradicted. And instead of having these troughs, you end up actually building a pressure dome in the middle of the room, a pleasure dome in the middle of the room. Sorry, I couldn't let that one go.
Or a terror dome.
A terror dome.
Yeah, there's
2 men into, 1 man leave.
And in fact, when it really works well, as you get close to the boundaries, the bass actually falls off, which is the inverse of what normally happens.
Yeah, that is not what happens to anybody naturally.
Yeah. So all bets are, not you don't have to move. So for years and years and years, all of us practicing acoustics, the word is practicing. It's just like doctors and attorneys. We're not really doing it. We're just practicing. Those of us practicing acoustics, it's like, well, you got to have the right ratios. It's a good idea to start with that. But if you're not starting with that, you can, by either building or commissioning the build of custom bass traps at the frequencies at which there are problems, 1, and then 2, placing multiple subwoofers in the room and optimizing them in ways that we can talk about in another session, you can actually get really good bass. So now your room probably has standing wave frequencies and locations that are different than what predictions show. I don't know if you've tried that. I don't know if you've done a calculation of it and said, well, I should have a problem at, I don't know, random number.
No, really. Yeah. I've never been able to get it to match up kind of to what the room does because of what you're talking about. Yeah.
Right. Plus there's stuff in the room. I'm assuming it's not totally empty. The stuff is going to vary it a little bit. So like I said, I could talk about this for 5 hours, and I actually have a scientific lecture that goes on for 5 or 6 hours about this with all kinds of data and experiments and charts and all this wonderful stuff. It's on whatever. You go I
like it. Consumer multiple subs. Well, let's go.
So check it out. You can have one big sub that's like a 15-inch or 18-inch sub, or 4 10-inch subs that are small and you can hide. Not that.
Or you can have 6 24-inch subs and then just lord it over everyone.
Oh, absolutely. You can do that. Absolutely. And I'll gladly sell you those along with the bridge over there. There's a bunch of solutions around this. All is not lost. And this is a great question, because in reality, when you look at the issues of acoustics and you go, well, you have this problem, this problem, this problem, this problem, the bass issue is the one that's the hardest one to resolve and is the one that plagues most people most of the time. It's also the one that once you solve it, you go, oh my God, the sound is so much better. You haven't changed anything in the mids and highs. Just getting that stuff from 15 hertz to 150 hertz to sound good is amazing overall in the pleasure of the room.
So to make the room the most pleasurable for bass, and I'm picking up on what you said, is your typical strategy to look at 15 to 150? Is that the range?
Yeah.
And so under 15, you're all like, don't really have to worry about it too much. It'll be whatever it is. Or
it's actually in your size room, that's under 50. Because
Really?
Below about 50 hertz in the size room you described, the standing waves stop to be an issue. The waves are all longer by multiples of the room. And so you'll notice that if you put a subwoofer in this room and you measure it anechoically outside, you just put a microphone in the cone, you bring it out on a nice day and you go, what does this thing do? You bring it into the room, you measure it in the room, you'll go, wow, it's exactly the same response as the anechoic response. And somewhere in your size room, somewhere around 50 hertz, 45, 50 hertz, you're going to start to see these swings. It could be plus and minus 15, 20 dB. So in reality, depending on the size of the room, the real problems are between 30 and 40 hertz up to about 100 hertz. That's really where, in the rooms we're talking about here, where the most issues are. The smaller the room, the more they move up in frequency. The larger the room, the more they move down in frequency.
And then if your room is large enough, they just go away.
I don't want to interrupt. I got a question for you, Anthony,
Yep.
if you don't mind. So when you're EQing, and I've heard this thrown around a couple of times recently, when you're EQing or calibrating a system in a room, do you calibrate the full spectrum of sound, or do you just calibrate up to the transitional frequencies?
Calibrate the whole spectrum of sound.
Okay. Okay.
Now, that's a whole discussion too. You know, we should
Okay.
do a session on calibration.
No, I mean, yeah, absolutely.
Yep. There is a, you know, there's a lot of legends in our industry, a lot. The only other
yes,
industry
sir.
where I've seen more legends is in nutrition. It's something I care about. You know, what do you eat? What don't you eat? So there's a
Right,
ton of legends. So one of the legends is you don't touch anything over 500 hertz.
Right.
Well, if you don't know what you're doing, you're right. You don't touch anything over 500 hertz. But the fact is that the room is going to change the tonal response of your speakers up well up into the 10 kilohertz range. And the type of equalization you're going to do above 500 hertz is more gentle. It's things that are going to be wider, broadband, to correct for the sound power of the speaker, how it's radiating in the room, and the returning sound power. You know, the speakers radiate a bubble of sound in the room, and the room returns its own bubble. And those two things together give you a certain spectrum at your ears. And it's not completely linear. The way your ear brain hears it is a little different than the way a microphone measures it. But just relying on knowing that the direct field of the speaker is smooth response and hoping the room doesn't change it, I've not found to work right. So I do tune all of the way up. The most radical corrections are usually below 500 hertz. And as you go up from that, it's relatively gentle things.
Okay. Very, very well said. Absolutely.
Cool. So we have questions that are slowly coming in now, but you also have a set of slides that you want to show as well. So what would you prefer to do? Get started into the slides or talk with people?
Let's take one question. I mean, you already gave me a question, and here we are 20 minutes into it, just yakking about this stuff, because it's important.
So let me
getting face right is important.
So Mr. Magali is with us, and he says, how do you deal with diffusion in the rear of the room or a room with a close listening position, only an 18-foot wide with rows of 4? So I'm not sure how deep this is, but maybe it's 2 rows of 4 and the second row is quite close to the rear. And what is a strategy for diffusion in that room, I guess?
So I think I'm going to paraphrase this, and Stephen, if I didn't quite get it right, please, send us another version. I'm thinking a room is 18 foot wide. You want to put diffusion in the back of the room, and then rows of 4. So what I'm thinking is maybe you have 2 rows of 4 seats is what I'm interpreting to this. So number 1, as opposed to what you're seeing in a lot of magazines, diffusion on the back wall and filling the whole back wall, bad idea. There you go. So now what? And I'll tell you why I say that. In the middle of the back wall, behind you, over a region of maybe 4 or 6 feet, you really want to absorb the energy. You don't want a lot of energy going back and forth between the front wall and the back wall. You want to absorb that. A lot of energy going this way is heard by your 2 ears as equal sound. Yep, 2 rows of 4 seats created, 20 feet long room. So sound going back and forth this way. Knowing that a diffuser is never perfect, a scattering device always leaves some energy in the orthogonal direction going on. Every time it hits your 2 ears, it's equal sound. And equal sound of the 2 ears means, I don't want to say mono, but center. It means it's in the middle. And we don't want that. We don't want the room to narrow up our sound field. That's not right. We want it to maintain whatever is the sound field coming out of the speakers. There's an amazing paper by Floyd Toole and Sean Olive, if I remember right, from 25 or 30 years ago called About Diffusion and Confusion, that goes into pages and pages of research on this that shows you don't do that, even though you'll see a lot of recording studios that do that. And they do that for tradition. They go, well, I saw that on the picture in a magazine, so I'll just keep replicating the error. So diffusion on the back wall is very nice, but over there and over there, and I'm going to, if I ever get to it in my slides, I'll show you that. So absorption in the middle of the back wall and diffusion to the outer part, so that the energy that's going back and forth like this is absorbed, and the energy that's traveling over in that direction hits something that scatters it, and then it bounces around and comes back this way. You like my interpretive modern dance?
All I know is that in my non-professionally designed DIY room, I did all absorption across the back because I was just suffering with so much echo inside of the room. So I got it half right. So maybe I should take the far edges and turn those into diffusers.
Take the first 3 or 4 feet off the edges. All absorption on the back, all absorption anywhere, I usually don't find to sound engaging. It gets in the way of the pleasure dome. So the pleasure dome, you arrive to. We're just going to keep using that, okay?
It's a new term, Anthony. This has to be a new professional term that you use.
In order to get there, like in all things of pleasure, you don't want to cause any disturbance. You want the whole pleasure to be like good all the way through. And if you have an entire surface that's dead, not returning any sound, your brain's like, what's going on? Why is there nothing coming from there? Your subconscious is doing, I know there's a boundary over there. Why is there nothing? And then it's like, is there something wrong? And it keeps unconsciously querying you into, this is not real. This is not real. I'm not in this movie. There's something wrong. So any surface in which there's too much absorption in any one area usually results in less believable immersion.
That's fantastic.
So that's a great question, and thank you for asking that. So let's go over to my little presentation over here, and please, feel free to interrupt. So this is a presentation about sound reflection control, and what do you do? How do you make it work? So now I have to figure out which screen I got to go to so that works. Yay! All right. Why talk about acoustics? Because we have a whole hour to do something on, and we just decided to talk about acoustics. What do you think? No, because I believe that acoustics affect sound quality way more than high-end cables, complicated power systems, esoteric amps, all of that stuff. They have an enormous effect. And at that, I'm being, what's the word? A little arrogant, which is, you can get all this really nice gear and you put it in a room with bad acoustics, it's not going to sound good. Actually, I just talked to a guy called Kareem. I don't know if he's on tonight or not, who's like, man, I've been messing with the speakers for years and the amps, and I put all this on, and then I got some of these modules, these absorbers, diffusers, bass traps, and I couldn't believe the difference it made. Way more than anything else I had tried. Mm-hmm. That's right. And I hope that at the end of today, you'll see why. So I like to say that the treating the acoustics or tuning the acoustics contributes to over 50% of the quality you're hearing. So even bad acoustics, Jiles, you were like, well, I have a room that's all square. What do I do? Well, it's fixable. You're not stuck with it. And in fact, it can save you money. You can, acoustical modules don't cost that much money. You can spend money on a $20,000 power amp and get virtually no change in the sound quality. And then you can spend $2,000 or $3,000 on absorbers or diffusers. And you're like, oh my God, it's night and day. So good way to do something useful. I like to think of acoustics as the interface between the speaker, the room, and the listener. It's this acoustical environment is a connection. And, in audio, we talk a lot about interfaces, those cables that you buy for lots of money to go connect this to that. It's nice to have a good cable, but that interface, that electronic interface, is not nearly as fraught with issues as the acoustical one. So let's look at that. I'm going to show you a few ideas in terms of what I mean by this interface. So imagine you're looking at a room from the top. This is a speaker over here. It's
a square room, I might point out.
It is a square room. Here's a speaker. It's wonderful. It's got a woofer cabinet and the horn sitting on the top. Lovely. And that speaker is going to send sound out into the room, and you're going to perceive the sound as this nice round event. Imagine it's like this really beautiful round sound, whatever you think is a round sound, a pleasurable round thing. And the direct sound is clear. The thing that goes from the speaker to your ears is unimpeded by the air in the room. There's no wind. There's nothing going on. It's nice and clear. Then there's a bounce off the left wall, which repeats the sound. So now you heard this initial sound, and then another sound is coming from over there, coming right behind it and causing essentially an echo, but not the echo the way we think of it. It's just a repeat of the same sound. The same waveform has just arrived at your ears from a different place a little later, and you're like, I don't know which one of these is the real sound. Then there's another one, and then there's another one, and then there's more reflections coming from the room, which result in a clouding and a blurring of the sound and through comb filters and repeated reflections. Do you hear it that way? Do you actually, like, imagine you're listening to the sound of a big drum being hit, boom, and you have those reflections. It still sounds like a drum, right? Mm-hmm. It doesn't suddenly going like, blah, blah, blah. Why? How is that possible when there's all these reflections? Hold that thought. So let's look at this. I'm going to contend that that reflections can be thought of as distortions. Here's an example of a saxophone. I play saxophone. Its sound is coming from the center speaker. It's reaching your ear. And then there's a reflection off the side wall, which is giving you two saxophones with one being delayed about 3 or 4 milliseconds. That could sound terrible. Hold that thought. I'm building a story here. So did you know that at the main seat of a typical listening room, so your room's 14 feet long, 14 and a half. How far back from the speaker are you sitting? You all the way on the back wall?
No, it's like 10 feet away.
10 feet away.
Well, 10 feet from the wall. So depending on which speaker, from the center, you're like 9.5 feet or something, depending if I'm reclined or not. So
is that room filled with 6 feet of dense fiberglass all the way around, or is it regular surfaces?
Just regular surfaces.
Surfaces.
So there is across the rear, I have 4, I guess 2 foot wide, 4 foot tall panels. So there's 8 feet width, 4 feet tall across the rear, and then a couple of panels at the first reflection points ish in the front as well.
Okay.
So
you have some absorption. So even though you have some treatment in there, the treatment's not 100% of the surface. It sounds like it's about 30%, 30 to 40%, maybe 30% of the surface.
Maybe 28, 27, something
20.
like that, yeah.
Okay. So did you know that even in your room with a fair amount of absorption, you're listening to more reflected sound than direct?
Makes sense.
Well, why? Well, check this out. This is the same room seen from above. There's a direct sound. There's a reflected sound. There's more reflected sound, more reflected sound, more reflected sound. And by the way, I didn't intend this, but this kind of looks like you from above.
It does, except I have given up on even comb overs.
Yeah.
And so I just
let it go.
Yeah, I have I guess the landing strip. No, like
yeah. So look at this. There's one direct sound vector from the speaker to you that's 9 feet, let's just say. Then there's another sound vector that hits this wall. Yes, it takes a little longer. With the extra distance, it's attenuated by maybe 2 or 3 dB. There's another one over here. And then there's another one, another one, another one. There's more reflected paths than there is direct path. Even though you're absorbing somewhat, you're not absorbing fully. There's still a fair amount of reflected path.
I feel like we're getting dangerously close to calculus.
I promise I won't go there. I won't even use the word integral.
Okay.
I won't use time constants, nothing. I promise.
Okay.
I'm tempted that I'm not. So we need to do something to reduce that ratio, reduce the reflected energy, not kill it. Okay. We want to just reduce it a little bit so that we're hearing a little bit more of the direct sound and in an orderly fashion. That's what we're going to talk about. We're going to talk about having a higher direct to reflected ratio than a normal room. Let's look at this a little more. What I'm doing is I'm kind of developing this a little bit more every time, and you'll see where I'm going. So,
and this is my room if it was a little more square. That's my bed layer.
Okay. So I'm expanding. Originally, I had one funky looking speaker. Now I actually have 7 speakers that look like wood laid all the way around you. It's still you in the middle when you still did comb overs. So here's the direct sound. Here's the reflections from the right wall. So there's one that missed you by about 10 degrees. It bounces around. After a bunch of bounces, it reaches you. Another 10 degrees further, it bounces around there, reaches you. Another 10 degrees further, it does 2 bounces. Another 10 degrees more bounces, et cetera, et cetera. And I'm just painting this out to about 50 or 60 degrees, I think. And then I'm stopping. So that's the direct sound. That's the off axis by 10 degrees, 20, 30, 40, 50, 60, out to 70. Okay. So there's one direct sound and 1, 2, 3, 4, 5, 6, 7, 8 reflected paths off the right wall. We add the left wall, we have another 8. So we have 16 reflected paths just looking in 10-degree increments. That's just the sidewalls. There's also the ceiling and the floor. The fact is, there are reflections from the right wall, reflections from the left wall, reflections from the ceiling, reflections from the floor. Ultimately, 75% of the energy going into your ear canal is energy that's left the speaker. A little bit's gone directly to you. A lot of it's bounced around the room and come back to you after the room has affected it. There's chaos. Your ear is hearing all these images of that original saxophone. Yet, you can still tell it's a saxophone. How do we do that?
Magic.
Magic. Well, magic
Voodoo.
actually is, we have an auditory system that focuses on the first arriving sound. We go, well, I heard that saxophone coming from there first, and then I heard it from there and there and there and there and there and there and there. I'll try to ignore that. It takes brain processing to like delete that. And you focus on what's called the first arriving sound, sometimes known as Haas effect or precedence effect. But it's a lot of energy, and that all happens with one speaker. Imagine now you're listening to a movie and all 7 speakers in this layer and then more speakers on the top are lighting up with all these reflected energies. At some point, your brain just goes, I don't know anymore, man. And it reverts into this interior immersive thing that just sounds like the same sounds coming from all of the speakers. And that is not the intended presentation. So, we do hear it coming from that first arriving place if there's just a few sounds. As you start to multiply the sources, it just gets confusing. So what do we do about that? The solutions are either using absorption, which is a material that sucks up the energy of the sound, which is actually by friction. The air molecules go in there and through friction through typically fibrous materials, it turns into heat. Or by scattering the sound. So rather than letting it bounce hard off the walls, you break it into little pieces. That's sometimes known as a diffuser. The broader sense of it is a scattering device that actually breaks the main wave that's going to the wall into little pieces that feels better.
And is that to attenuate the volume of the sound? So it scatters, diffuses, each subsequent scattering is at a lower volume, so it has less impact.
Right. So let's pretend there was a scattering device right here. Okay. Imagine there was one right here. The sound that's over here, rather than bounce as a coherent wave back to you, just delayed, now gets hit there and it breaks into little pieces where the sound going to your ear is 6 to 10 dB lower than if it just bounced directly. A really good diffuser, really impossibly good diffuser would break it down 10 to 12, almost unattainable. Usually 6 is a great start, 6 being a quarter of the power. Okay, so that's the idea. And I'm going to talk about diffusers plenty. And I'm glad we started with that question because I'm an enormous fan of using diffusers. To me, it feels like it's you'll see what I mean. It's what takes a good sounding room to an excellent sounding room is the right scattering devices in the right places. So ultimately, what's the goal? This is a room, this is the same room treated with treatments, and we're going to build this. In this room, I've put an absorber, another absorber, another absorber, another absorber, just covered about 15 or 20% of the walls on the right. On the left, I put some diffusers interleaved in them. When you do it all right, when it's all working right, you get this sense. You get a really clear sense of where the sound's coming from, and then you get a sense that you're enveloped with energy around in the room. So there's a clear, direct sound, and there's a sense of immersion without distracting from any of the walls, without causing loss of articulation, which is usually, I can't understand the dialogue, or I didn't really hear where that car went, or yeah, I just heard that there was an explosion here, but I couldn't really localize it. When it's all done right, you can clearly hear where the direct sounds are, and it's accompanied by the sense that you're bathing in the sound field. I call this the crescent of sound. We'll now call it the pleasure crescent.
The pleasure. Someone had mentioned it before, and I thought, well, here we go. I thought he said the famous croissant.
Croissant.
Yeah, croissant.
It's really croissant. And by the way, when you put chocolate in it, it's called a pain au chocolat, bread with chocolate, not a chocolate croissant, because they're not in a crescent shape anymore. There, you learned something new today. As you know, I'm a big chocoholic.
Yes, you are.
All right. Now, so done? No. What do we do? How do we get there? What? Cool. Do I just go buy a whole bunch of absorbers and diffusers and throw them everywhere? No. So the next part of this discussion. So actually, I like to summarize once in a while. Part 1, in a typical listening room, there's more reflected energy than direct sound, and it just makes your life difficult in terms of clarity, articulation, localization, dialogue, clarity, all of that stuff. It just suffers. We don't want that. We still hear where it's coming from because the brain's processing out the reflections the way a microphone doesn't. By the way, I think everybody's had the experience of trying to record something in a room, or playing, just sticking out your phone in the room, and you notice how much reverb and echo there is. The ear brain processes it out, but let's not tax the ear brain. I want to sit down for 2 hours of a movie and not have to do anything, just relax and enjoy the movie. So the idea is to have the croissant around you. That's all nice and pleasant. How do we get there? So I'm going to introduce this concept of reflection decay time. So this is another version of the same diagram. There's a bunch of reflections. In acoustics, they're not counted by the amount of reflection versus the amount of direct sound, unfortunately. There are some predictive math systems and some measurement systems that say, hey, your ratio of the direct sound to the reflected sound is this percentage, and the early reflections are this, the late reflections are that. That would be really cool. Most of the conversations and most of the analysis systems just talk about the time it takes for all the reflections to die down. It's a bit too global, but that's what we got. So the reflection decay time, sometimes known as reverb, but that's actually an inaccurate term, is a result of multiple reflections. And it has to be just right for everybody to go, Jiles, your room sounds amazing. Don, I can't wait to watch another movie or listen to another concert in here because it just sounds awesome. What is that just right? Is it right because I say so? No.
Tell us why. Tell us.
I'll tell you why.
I have to know.
So just right, when it's just wrong, it could look like this. So here's a diagram that we often talk about in acoustics, which is an impulse response. You put an impulse into the room. This is not actually the way an impulse response looks, but it's a sort of formulaic. You put an impulse in the room like a thwack. Used to be that people would actually pop a balloon or fire a gun in the room, which is an impulsive sound. And they would look over a histogram. They would look at when those sounds would come back through the measurement system. So imagine you have, your room, there's an initial thwack, then there's some reflections, maybe off the side wall, off the ceiling floor, off the back wall. Then there's another group of reflections later, another group of reflections later, but then there's all these time gaps in there. And the time is, in the case of this, is about 0.4 seconds. So after 0.4 seconds in your room, Jiles, and this happens to be about the same volume as I've designed this for, the sound finally dies out. That's called the reflection decay time. Mm-hmm. It's too long and it's chaotic. Chaotic means that there's one sound and then there's a group of sounds and another group of sounds, another group of sounds, and your brain's kind of being like, I was going to use the wrong word because, we're trying to stay clean. You're being offended. Like, oh my God, I'm hearing something here. No, it's here. No, it's here. That's not a good way to enjoy movie. It's not a good way to get the pleasure room happening. More better than that is this, is to affect an overall treatment system in which there is a direct sound. I'll compare this to that. Same direct sound. The reflected energy is still in the room. It's attenuated and it's really nice and smooth over time. So imagine what your brain does. It gets a direct sound, and then it gets some gentle reflections that come from all these different places, but none of them are too strong. None of them are clustered together. None of them are distracting you. And then eventually at your 60 dB down from the direct sound at about 0.32 seconds. This would be for a room that's about 350 to 400 square feet. This is ideal. How do we get there? So let's talk about that. So ideally, the reflection decay time would be between 0.2 and 0.4 seconds, depending on the room size. How did I come up with that? I always like saying this. Research shows that most people like that range of decay time. What research? Well, about 35 or 40 years ago, a bunch of people got a bunch of grant money from a bunch of governments in a bunch of countries where they made a lot of loudspeakers and where they wanted to go, well, how do we build a listening room that we can listen to our speakers in and know they're going to sound good to most people? Well, let's come up with a standard room. It's the IEC standard listening room. And the whole idea is like, well, how much reflection decay time should there be? What's the ideal time? So the researchers got a bunch of listeners, put them in a bunch of rooms with a bunch of different acoustic panels and said, well, do you like this better? Do you like that better? Do you like this better? Do you like that better? And what they found is that in small rooms, people liked a treatment that led to a pretty short decay time of about 0.2 seconds. A small room may be 200 square feet. In a 400 or 500 square foot room, they liked it better when the decay time was about 0.4 seconds. That's a 2-to-1 ratio.
That's a big difference.
Big difference. Where does that come from? It's not because I say so. Actually, I'm just using the research that was done back then by a consortium of people that did the work. I just happen to have tried it, and I go, yeah, that works, man. I've done this 1,200 times since I started the design company 25 years ago, and if you follow those guidelines and you listen to the same damn pieces of program material and other ones, it always ends up sounding really good. Now, to get the real number, there's this calculation. I'm not doing derivatives.
Yeah, this is easy.
This is easy.
Yeah,
so I do this in my sleep. This is the calculation. If you know the volume of your room, which is length multiplied by width multiplied by height, and you take those three, that's the volume of the room. You divide that by 3,532, and then you take the cube root. The cube root is the one that looks like a square root, but it has a little 3. And then you multiply that by 0.3, you will find your target reflection decay time.
What is the 35, 32 constant in there?
It's a constant that they come. So the researchers said, okay, we have all the statistics that says that people in a pretty nice tight statistic said in this room volume, we like the decay time here by putting this many absorbers and diffusers in the room. In that one, we liked it there. And this one, they would liked it there. So they looked for an empirical curve that fit that statistic. And they found here's a curve that fits that statistic.
Gotcha.
So if you take a room, I'm hoping I'm remembering this right, but if you take a room that's somewhere around 22 by 16 or 17 by 9, here, I'll do that live. And you multiply that. So what did I say? 22 by 17 by 9 is 3,366. Close enough. Okay. And you take that volume. Let's just say I actually had the right number and gave you that number that ended up being 3,032. Just pretty close. That the volume divided by that would be 1. The cube root of 1 is
1.
0.3 times 1 is
0.3 of 1. Yeah.
0.3 times 1 is 0.3. So if you had a room that was about 22 feet long by about 16 or 17 foot wide by 9 feet tall, your target decay time that would allow you to bring 30 of your friends over and 29 of them would go, I like the sound in here. One of them's, whatever. We don't care about that person. You build a room on this. If you're listening from, somebody came from Japan. It called in from Okinawa. In the metric system, it's a lot easier. The volume is divided by 100.
Oh, wow. Nice.
So a 3,500 cubic foot room happens to be 100 cubic meters. Same calculation. So
I think they just made that number up. I think 100 metric. Let's go.
Do you have no idea in high level science how much stuff is just made up empirically, like close enough? I talked to somebody who's older and who was in NASA during the Apollo program. And he said, you have no idea how many things we just had to wing.
Yeah.
Wow. And, good engineers, good technicians, things get wung. I guess that's the past tense of wing.
They got wung. Yes, they got
wung. And, if you knew what you're doing, you can wung it. But anyway, these numbers, I'll confirm, having done hundreds of rooms based on this, I'll confirm this works. You have a right balance between articulation. The imaging is good. The spaciousness is good. It's not just all washed out. It's not all like a tiny little image that has no spaciousness for 2-channel. When you're doing multi-channel, you can actually hear the sounds going around, but you don't hear the individual speakers. Everything just falls into place really nicely if you follow this guideline. Now, you could do this math, or you can go, you know what? If I just cover about 15 to 20% of my wall surface with absorbers, I'm going to get there, and I'm going to prove that to you. This last rule of thumb is a lot easier. So bottom line, this is actually an inaccurate way because the numbers are not linear, but the target decay time in the room goes up with room volume. Okay.
Sure.
From about 0.2 to 0.4, depending on your size of your room. If you really want to know what it is, just put it on that equation. Now, the decay time at what frequency? Like when you put 1 kilohertz boop into the room, you want it to fall down about 0.3 seconds. Let's say it's that room that's 3,000 cubic feet. But you also want 4 kilohertz, high frequency sounds. You want 8 kilohertz to fall off at the same way. You want 100 hertz to fall off at the same way. You want all the frequencies of all the sounds you put in the room to decay down evenly and fall down into nothing at the same time. That gets a little harder, because now you have to have a treatment system that covers all these frequencies evenly all the way around. So a lot of people don't talk about that, but it's really important that the sounds that go into the room, pass your ear, bounce around, all die out evenly with frequency. And most rooms, if you measure them, fall off faster at some frequencies than other.
Mhm.
And that means that the sounds that die out faster disappear faster. The ones that stay longer give an emphasis to the room. That's like cranking up the
Yep.
tonal balance in that region. It just hangs longer. So good news is it doesn't have to be perfect. The accepted rules are usually, between about 100 hertz and 4 kilohertz. You want it to be about the same. Then it's okay for it to rise up to where down to 60 hertz, if it's twice as much. So if the target was 0.3 and you let it rise up to 0.6 at 60 hertz, your buddies are still going to like you. And at the high frequency above 48 kilohertz, if it falls down from 0.3 to 0.15, nobody's going to be offended. They're not going to run screaming. So getting it right is you got to use the right amount of absorbers to control the mids and highs. You want to use the right amount of bass absorbers to control the lows. And those are kind of different devices. There are certain topologies that work well for bass, others that work well for highs. If you really want to know, you can calculate that using one of these three equations, the Sabine, Eyring, or Arau-Puchades equation. You ready for this?
I'm so ready.
So this is a Sabine equation, which is back from the 1930s. The target decay time should be 0.049 times the volume of the room divided by the absorption surface area and by the absorption coefficient of your panels. That's not that hard to calculate.
That's not that bad. Yeah.
That's not that bad. It's a bit inaccurate. It's very global. And so later a guy called Eyring did, we really need to do this ratiometrically. So this is the volume of the room divided by the room surface area, but then the natural log of the 1 minus the area weighted average absorption coefficient. So if you have a wall with an absorption coefficient of 0 and a panel with a coefficient of 0.8, you want to area weight that and you'll get more accurate. Pretty good. This is a little harder to calculate. And then in the 80s, a guy from Spain called Arau-Puchades from the Barcelona area came up with, you really need to break this up into what's going on the front to back axis, the left to right axis, and the ceiling axis, because those axes are not the same in most rooms. And so that same equation as the Eyring is now separated along those three axes, and you end up with this really complicated thing. And the math whizzes in the room, in the virtual room, will relish this. They'll build a spreadsheet and do all of this other stuff, and they'll be at it for a while. I got to warn you, you'll start using so many coefficients in Excel that you'll get close to a point where it goes, can't do it. And this is what we do. When we actually calculate a room, we have this giant Excel spreadsheet that we put all the dimensions, all the surfaces, all the different materials, and it goes and number crunches it. And after doing it a whole bunch of times, after doing it about 200 or 300 times, we found that, hey, most of the time, the big machine, the machine that goes ping, you remember that from a really long time ago, told us that you had to cover the walls with about 15% of absorption. It's like, I detect a trend. This StreamYard session, this webinar is called Trends in Home Theater. Well, the trend we detected is, hey, in general, if we just cover it with 15%, it's going to get pretty close. That's it. So don't put too many absorbers on your side walls, your front wall, your ceiling, and your back wall. Covering the whole back wall is too much of a dead area, only 15%. And then if you can, cover another 15 or 20% with some kind of scattering device, because it improves the sense of spaciousness. And I'll break that. I'll get to that quite soon. We only have 10 minutes to go, but there's what I call a 2D diffuser, which is a diffuser, a scattering device that when the sound hits it, it re-radiates only on 2 dimensions on a plane. sometimes known as a hemi-disc. And then there's a 3D diffuser, as I call it, which is a panel that the sound hits it, it re-radiates in 3 dimensions hemispherically. I like those towards the back of the room, and I like the hemi-disc ones towards the front portions of the room. I like to spread the absorbers around the room evenly, not all clustered in one place, but distributed in panels that are either 2x2 or 2x4. And I like to interleave absorbers and diffusers around. There's some amount of bias in some places, but it's pretty close. I also have found that you want to lay things out so that you do encourage some amount of lateral reflections by putting a fair amount of diffusers on the side walls and not so much on the back wall. You want energy traveling this way because that tells your brain that the room is bigger than it really is. I've also found that asymmetrical layouts work better. Strangely enough, when you have an absorber here and across the room, slightly offset is another absorber. Like if the absorber is 2 feet, you offset it by a foot or more, and then you have a diffuser. It's actually slightly asymmetrical, and that introduces a bigger sense of spaciousness for reasons we can talk about later. So
more like real life. Yeah.
More like real life. That's how real life is. Don't forget to treat the ceiling and make sure you use base absorption. So I get a lot of people calling me to go, I got a bunch of panels. I put them on the wall. They're all 1 inch thick. It's great. And it doesn't sound good. Well, you're not treating the base. You're treating down to 1 kilohertz. That doesn't work. So, this is a proposed layout. Jiles, we're going to go for another 8 minutes and then we'll reconnect. Okay.
We can go a little bit longer if we need to get your complete thought out.
Okay, let me finish my complete thought. This is a proposed layout that yields what I'm talking about. Seen from the top. First of all, instead of having a blank ceiling, I would recommend putting some absorption in that place between the front speakers and your seating position to basically control that energy that's in the front half of the room. Notice that those 3 panels are a small portion of that ceiling. I also recommend putting some scattering devices, some diffusers up on the ceiling above you or slightly behind you, not in the front part, but in the back, so that the surround speakers can light that up and you get this really nice immersion from the top speakers and the side speakers. I like to recommend, if we look at the left wall, there's 3 absorbers. So imagine the left wall is made out of 3 absorber panels, 2x4, that when you take them off before you put them on the wall and you just line them up, look at how much of this room it takes. Like a quarter of the room would be this much, but it's less than that. It's only 15 to 20%. And lay those out evenly in the room and then put some 2D diffusers that could be the shape of a cylinder or shape of a slatted diffuser. There's a bunch of different ways on the front half of the room, and on the back half of the room, put some 3D diffusers. This shows the front speakers behind an acoustically transparent screen. This shows a surround speaker. You should have a driver pointing at you, but that shows a surround speaker. I'll talk about the bass absorbers in a second here. The other wall, same kind of thing. Absorber. We're doing one more here on the door, a thin one. But same thing, not a lot of them, some diffusers, 2D and 3D. They are similar in their locations, but not the same. There's an absorber here. There's a diffuser across the room to introduce that asymmetry. And then the back wall is absorbers in the middle and diffusers on the outer part, maybe a diffuser up high. That is a layout we've done after lots of research and lots of trial and error. That's a layout that works. That's a recipe that generally gives us a really nice pleasure room. Now, in addition to those absorbers, we do want to have some bass absorbers, some devices that absorb down at the lower frequencies. They don't really absorb anything above 200 or 300 hertz. They're really working from 200 hertz down to 40 hertz. You usually place those in the corners. That's where they work the best. So some bass absorbers in the room, and there you go. Okay. And if you do that and you look in detail at what happened, this is the direct sound. This is a reflection that gets absorbed. This is a reflection that gets scattered, a reflection that gets absorbed, one that gets scattered, absorbed, scattered. If you follow those lines, you'll see where they go. So all the off-axis sounds, some of them are absorbed, some of them are reflected actually from surfaces that are untreated, and some of them are scattered. And from this, you end up with our famous croissant, our buttery croissant, a beautiful pleasure sound.
So buttery.
So guys, let me just tell you, I've heard a few different rooms that Anthony's designed, usually at Cedia, But he did the design for Gene Delasala at Audioholics room that we all put together, and it was amazing. It's still one of the best acoustic layouts I've ever listened to. It's wonderful. I think so.
Thank you, Don. Appreciate it. I was actually at his room again a few weeks ago, and is like, man, your room sounds good. It really is.
It's great.
Gene did amazing work with the subwoofer waves, a really complicated subwoofer thing. It took us about 12 hours of tweaking all the subwoofers until they all worked cohesively and got it to work. Well, you heard it since then. But the rest of it, the imaging, the clarity, everything just sounds amazing.
It's a cool space. I'm really proud of it. Everybody put a lot of work into it.
So I'm going to switch in the next few minutes. I'm going to switch a little bit into sales mode if I can. I jokingly call this propaganda. Not all propaganda is false. Some of it is actually real. So I actually had a whole module, and I'm more than happy to come back and do this at some point, where I describe all the different types of absorbers that exist on the market or in the science, all the different types of diffusers, and explain how they work, and all the different types of bass absorbers, sometimes known as bass traps. I'm more than happy to dedicate another half hour or hour on that. It'd be fun. But I'm going to fast forward and go, here's all the things we've done to provide solutions to these issues. So there's a company actually based out of Croatia called Sonitus. A great company started by a rock and roll drummer who in the early days in Croatia found that he couldn't buy any acoustical treatments because there was nothing in the country. So he just made his own. And then he made a few more for some friends. And now he's got a giant factory that cranks these things out. We happen to be the US and North American and South American distributor for this stuff. It's really good. So there's absorbers. One of the absorbers is called Legato. It's a really nice, it's a dense polyester. It's not polyurethane. It's a much heavier material with much more tortuosity. That's the term to say, here's how much friction it produces to, did you know that word, tortuosity?
I thought it was something about a turtle.
It's not about turtles. It's about torture. It's torturing the sound waves to be dissipated through heat.
I like it.
So it's a chunk basically of this polyester foam that's covered with a velvet finish. It's actually flocked on there. It comes in many colors. It's 2 foot by 2 foot, 60 by 60 centimeters. It's 3 inches thick, 8 centimeters. There's also a 5-inch thick version. One's called Legato 8 for the 8 centimeters, and the other one's called Legato 12 for 12 centimeters. The Legato 8 works down to 250 hertz, and the 12 works down to 160 hertz. And right around now, anybody who really knows acoustics should go, okay, there's some lying propaganda. There's no way a 3-inch panel can work down to 250 hertz. Physics don't allow it. You're right. If it's just a frictional material. You're completely right. But this layer that's actually flocked on top is slightly what's called tympanic. It provides a little bit of flexural absorption that when you tap it, you actually hear the tympanic character of it, also known sometimes as a bass trap. So it's a mid bass trap. So around 200 to 250 hertz, it has some absorption through flexure. And then at about 400 or 500 hertz on up, it's a frictional absorber. And that's how we get the extra half octave down below there. Anytime, by the way, any of you guys think I'm telling lies, please bring it up. I always want to address it. And then either I was misinformed or there's a little more to the information. So anyway, there's 2 different sizes, a thicker one and a thinner one. The thicker one costs more money. And they come in any color you want, except in the US right now, we have only available black, gray, and white. In Europe, you can get them in blues and reds and yellows and all these different colors. And I imported a bunch of those and nobody bought them over here because we're just boring. A little too conservative in the colors. Another really cool absorbers is the Wave X absorber. It's sculptured dense polyester foam. It's available in black and white. It's also 60 by 60, 2 foot by 2 foot. It's a little thicker. It's 10 centimeters thick, 4 inches thick, and it ranges from 200 hertz to 20 kilohertz. Again, normally 4 inches would only work down to about 250 to 300 hertz. The top layers on this is this special little material that's it's sort of semi-rigid. When you tap it, you'll actually hear it has a bit of a resonance. So there's a bit of a flexural absorption, black or white. When they're on the wall, you can line them up this way. You can line them vertically, and there's a really cool look to it. It's very studio-y. It's very edgy. If that's the look you like, go for it. There's a much simpler absorber made out of dense polyester foam. It's just the straight foam without a finish on it. It's 24 by 24, 3 inches thick. It works down to 315 hertz. It does not have that extra flexural absorption to it. Another absorber is called Canvas. It's a solid wood frame filled with the same polyester foam and a really nice set of fabrics. There's different colors available. And it's right now in our stock in the US, it's black or white. Other countries have other colors. It's 4 foot by 2 feet, 120 by 60 centimeters, 6 centimeters thick, and it works down to 200 hertz. If you actually hang it from the ceiling with an air gap, or if you place it on the wall with a bit of an air gap behind it, black or white. All right, switching gears. We have another set of panels that are I'm going to call them mid-frequency to slight bass absorbers. So this is the same dense polyester material, but there's a wood material on the front that's then slotted for decorative purposes, but it also rejects some high frequencies. So the range of absorption of this is all the way down to 200 because that front layer acts a bit like a flexural absorber and a Helmholtz absorber. That's what I skipped in my lecture on absorbers. So this is not just a frictional absorber. It's a combination of a frictional absorber, which is just something that the air molecules friction up into, a flexural absorber, which is a thing that bends and absorbs that way, and a little bit of a Helmholtz type absorber where the holes actually, with the resonance of the energy behind it, absorb some of the energy. So it works down to 200 hertz, only works up to 3 kilohertz. And you go, well, what about above that? Well, sometimes you don't want to over absorb the highs. A lot of rooms naturally have high frequency absorption by the carpets, the drapes that may be in the room. So a lot of rooms I go into with no actual treatments, but a lot of furniture have pretty dead high frequency, and the mid-range is at 0.8 seconds. Well, in a room like that, you would want to pull down the mid-range, and you do that by using panels like these. So these have a tapered high frequency response for the reason I just mentioned. So they come with different finishes, different looks. There's, different styles, one for anybody. And actually one of these is hanging behind Dawn.
Right here.
Right over there.
Right there.
Right there. So, all right. Just a few more things. Thank you for staying a few extra minutes here. So, continuing on down the frequency. So I started with mid and high frequency absorbers, went to this kind of low mid absorber, kind of edging on bass. And then we have some bass absorbers, which we call the deco traps. Deco because they're decorative, traps because they're sort of a bass trap. So they're usually corner mounted. It's a thick section of this dense polyester with a wood panel in the front of which that has some slots. And that whole thing acts like a flexural bass trap. You put it in the corner. Its main center of action is around 70 to 80 hertz, which is where most of the low frequency mumbling comes from in rooms. If you listen to speakers in rooms that sound great outside, you bring them inside, you'll notice there's a lot of energy there. That's what takes care of that. They don't absorb a lot of mids and highs. It's really just in the bass region. There's a bunch of different finishes and styles. The maze, actually there's also some of the other styles there, different colors. For more info on all this, go to the website. I'll show you later. Okay. Any questions so far? All good?
It's all making sense.
Now, all of these things, I won't announce any prices because I can't remember them, but they're all really cost effective. They're in the, $50 for the cheapest things up to 80 or $90 for the more expensive ones. It's all really well priced. All right. We started this whole conversation today with diffusers. I'm a big fan of them. Thank you for asking that question. I do think that after you're done taming a room with absorption, if you want the next grade, that next thing to get it like really nice, put some scattering panels, also diffusers. So we got a bunch of different models. The basic one is called a 4-fuser. It's basically a slot or a slot type diffuser made out of hard expanded polystyrene painted with a hard acrylic paint. You would usually put those from your seat position on the sidewall, from your seat position forward, maybe a few on the ceiling if you want. They work from 600 hertz to 4 kilohertz. Not expensive. Next step up as a 3D diffuser, this is what I call a 2D diffuser, because the sound that would hit this would scatter only horizontally. You turn it this way and the sound would scatter vertically. Mm-hmm. This is a 3D diffuser. When the sound hits this, it bounces in all directions hemispherically. It's 2 feet by 2 feet. It is 6 inches deep. So it takes up a pretty big chunk of space. Why so deep? The lecture I had on diffusion explains why you want something that's deep enough for the wavelengths to actually be properly captured and scattered back out. We'll get back to that. So by being 6 inches deep, it works down to 400 hertz, which is important. Diffusion is not only necessary at high frequencies, you really want it into the mid-range. So the sound of voices and other sounds in musical instruments and in film soundtracks are all well controlled down into the mid-range. And you can get it in any color as long as it's black, white, or gray.
Nice.
I've had people buy those and repaint them. Just a light coat of either acrylic paint or latex paint. You can paint them any color you want. I think Gene painted his.
I painted his. It's a special paint. It's for foam. Yeah, I painted them all like a brown. It turned out nice, but yeah, it's a special paint you can get on Amazon for painting foam. It won't melt it.
Right. Exactly. So we have two versions of the Big Fuser: Big Fuser 1, the Big Fuser 2. Different form factors, same acoustic results, same depth, same size. Somebody likes this look better, the curved size better, and the next person goes, nope, I don't like that, I like this. And there's tastes great, less filling kind of thing. We have both, but you can get them as any color as long as it's black, white, or gray. All right, there's the white. So we also have the Big Fuser in solid wood. That thing weighs about 40 pounds. It's all solid European oak. When you mount that on the wall, make sure you use really good sized toggle bolts because it's heavy. Looks gorgeous. So if you have aesthetic considerations, I gotta be honest and fair. This is painted styrofoam. Okay. And if it's in a dark room in the dark and you don't care, all fine. It's not as pretty as this.
Oh, yeah.
This costs more. You get what you pay for. Acoustically, it's really similar in performance. This works a little bit better down into the lower frequencies because it's a harder material. There it is. This is really about aesthetics and a little bit of performance. And those are available in different wood finishes. Finally, we have some combination panels that we're just introducing. So there's a product called a 6-strip, which is a combination of a 2D diffuser and an absorber. It's actually a wood enclosure with slats, and inside behind the slats is a dense billet of that flocked polyester foam. It's 24 by 24. It's 3 inches deep. It scatters from about 1,000 hertz up to about 6 kilohertz, and it absorbs down to about 250 hertz and up to only 3 kilohertz. So what's interesting with this is if you actually don't want to put all these absorbers and diffusers, is if you use a bunch of these around the sidewalls, you'll get the right combination of the two.
Interesting. Right on.
Yeah. And it's available in any color you want as long as it's oak or black.
Nice.
All right. Then there's this new thing we're just introducing called Archwood. This is very cool looking. It's a curved panel, basically the same kind of constitution as the decozorbers we talked about earlier on, but instead of 2x2, it's 2x4, and it has a curved shape. So it absorbs, it's 4 inches thick, 10 centimeters. It absorbs pretty well down to 200 hertz because of its thickness and its tympanic character, and it provides scattering in the lower frequencies. It's not a very sharp diffuser. It's big, it scatters big, wide wave fronts. Put a bunch of them in the room. They look like this. It's a cool solution to get low, mid, and mid frequency absorption with some amount of scattering and a really cool look in the room.
It does look cool.
So I have a whole series of things I'm going to skip through, but this is a room with a solution using the premium approaches. the ultra approaches. We're out of time for that. I did want to show you some pictures. So is it okay to mention Gene on this?
Yeah. Oh yeah, we're all friends. That's
Old
Gene.
friends. Gene
Absolutely,
Dillis.
for sure.
This is
100%.
Gene's room with his giant speakers. Is it okay to mention brands?
RBH.
RBH is, yep.
I
Looks
never
like
know.
RBH to me.
It's like really nice RBH speaker. Very complicated system, wide range, very nicely designed. And it on the sidewalls is a combination of the Legato 12s, the 4 fusers, and the big fusers. I find out today painted by Don, the man.
Wow. Yeah.
This is looking, on the sidewall, but you see that layout where there's some absorbers, some diffusers, some absorbers, some diffusers, a surround speaker, more absorbers. Not all the absorbers in one place, not all the diffusers in the place. It's a nice even scattering. This is a totally different space in which we've got a combination of 6 strips and absorbers, pretty sparse layout. Okay, not a lot of over treatment. The room looks amazing. The pictures, sometimes I know photographers that do an amazing job at capturing a room. I'm not that good at it. These pictures were all taken with my phone, okay? But this room looks gorgeous. It also has some deco absorbers on the back. It works out well. This is another listening room with a combination of 6 strips and wood, big fusers, and some of the legatos.
So Anthony, real quick, not to interrupt you, but I think this would be of huge benefit. We've been talking, as an integrator, a lot of systems we do are open floor plans, great rooms. Could you, next time we get together on here, put a little something together about how to, get these rooms that aren't enclosed or they're open? Yeah. That would be immensely helpful because that represents a big part of the audience.
Yeah. So if and when we can reconnect, if you'll have me back, I'll prepare.
We have you scheduled for half an hour already, but I think we will need to add another time in the August time frame.
Okay.
So we can figure that out though.
Yeah, we can go through
beautiful. Wow.
So
this is nice.
This is a room that's not quite finished. The grills on these are our speakers, Grimani system speakers. There's grills that are supposed to go on there. When I went over to calibrate it, the grills weren't finished by the carpenter, but this is gorgeous, right? So 6 strip
ceiling
absorber, slatted ceiling with some diffusers, some absorbers. Really beautiful. The whole house is very, very modern, very sleek. This is looking back in the other direction. These are some of our Grimani Rixos S speakers. Diffusers up on the ceiling.
On the glass, any like motorized shades?
There are shades on the glass. You can't quite see it there, but yeah, there's some of the duet model shades that come down. They're the plated ones that provide some decent absorption. So
right on. Very
and
cool.
This is another room where more of the same kind of way to go about that. So enough of that. Stop screen. There we go. So I've gone over. We had some great conversations. The initial question on diffusion, I think, was it Matthew, if I remember right? Andrew. Like somebody asked, "Do you feel like you got your answer from that?" Maybe
Steven.
I hope so.
Stephen McGauley.
Yeah. So I hope you got your answer. I know I skimmed through it really, really quickly. Sorry about that. But when we come back about the theory of placement of all these things, you'll see, I had that one drawing that showed what I like to do on the back wall, which is absorption in the middle and then 3D diffusers towards the outside. That's what I wanted to cover. We gone there. All right.
Right on.
Anthony, thanks for sharing all this because I know how hard you work, secondhand, but I know and how busy you are. And you always put these presentations and share it, which is great. So
cool.
Thank
you. Yeah, I like doing that. It's a picture is worth a million words in this whole thing rather than just wave around a lot. I like doing that. So.
Absolutely.
So I'll echo that sentiment. Thank you so much. Everyone's time is precious. And I appreciate both you joining as a guest, Don joining as my illustrious co-host, and then everyone out in the audience spending their time here with us as well. Without the folks out there, there'd be no one for us to talk to. So we appreciate you joining us and spending time with us.
Great to see you.
Can I bring up one last thing?
Absolutely.
Don, Do you have some lights here? Do you have anything?
Oh, I do, but I just pulled the plug out, and I don't have the dexterity in my fingers. Yeah, next
Oh,
time.
never
Yeah,
mind.
my
Don
battery
has
pack
something really
came
cool.
out.
Never mind. You'll have to show
Yeah,
that.
yeah, I would be lighting it up, but
That whole
it's
thing
good to
down
see
there,
everybody.
this beautiful blue color. I love it.
There is a video for those that subscribe to Don on your Instagram feed, I think it was, or was it Facebook?
Yeah, on my YouTube, whatever. It's just
Was it on
silly.
YouTube? All right. So fine. And that will lead to the final closing thoughts here. For those that have not subscribed, please click on the subscribe button if you've made it here on my channel, which I think is the only place where we're streaming at right now. Maybe we're on Don's we're on Don's as well. So if you're here via my channel, please go look for Digital Don AV on YouTube. And if you're here via Don's channel, please look for @Jiles McCoy on YouTube. And Anthony, do you have a dedicated YouTube channel or socials that you'd like to call out?
Yeah. So actually, I should bring that back up. That was all the way at the end. So
let's bring it back up. Yeah, let's show everybody. And I will add this to the notes as well, so people can find it there. But yeah, let's do. If you reshare that, I'll bring it back up on the screen so everybody can see.
Bada bing, bada boom, over here, entire screen 1, bing. So here are the websites for the three companies. You'll look there. When you go there, you'll actually see the YouTube links and all of the other socials. But certainly, if you poke around on any of the socials and you look for the three companies, you'll find them. We have that on there. So you'll find out a lot. Some of what I'm talking about over here is also in little snippets of YouTube recordings on there, so you can learn more right there.
Awesome. All right. I think with that, we've exhausted our time for the day. Everybody, again, one more time, thank you so much. And remember, we do this every week, Tuesday nights at 8 p.m. Mountain, 9 p.m. Central, 10 p.m. Eastern, and 7 p.m. Pacific. We'll see you next week. Thanks, everybody.
Thank you.